Okay, continuing with our series of questions from TMUA 2016. This is paper 2, question 11. So here it talks about a polynomial, f of x, with real coefficients. And it has exactly two real roots at minus p and p, where p is positive. And then it asks us to consider three statements and asks us which of the above statements must be true. So some observations. It talks about a polynomial, f of x, a polynomial. So a polynomial is an expression where you've got coefficients of powers of x. And those powers of x, their powers must be positive integers to make it a polynomial. Okay, and then it talks about which of the statements must be true. So either the first is true, the second is true, or the third is true, or some combination of those three is true. So it says the statement number one, f prime of x is 0 for exactly one value of x between minus p and p. Exactly one. So it doesn't tell us, it says it's a polynomial, but it doesn't tell us whether it's a quadratic, a cubic, quartic, etc. So we can't make any assumptions as to what the highest power of x is. So when it says there's a root at minus p and p, there's nothing to say that it hasn't got lots of turning points between the two roots. So this could be some sort of polynomial, and we've actually got 1, 2, 3, 4, 5 turning points between minus p and plus p. So that suggests that exactly one value for the turning. This represents the turning points. That's not necessarily true. So that's not a must at all. It would be if it was quadratic, maybe. Well, it would be if it's a quadratic, but anything else, and clearly it's not true. Part 2. The area between the curve and the x-axis and the line x equals minus p and plus p is given by twice the area from 0 to p. So an example of what that might look like, you definitely need symmetry around the line x equals 0. So if you had something along the lines of this, something that's supposed to be symmetric about there, that's your minus p and your plus p. Clearly, the idea that they're suggesting is that area there is the same as that area there. But, of course, in reality, it needn't be. You could have something else where the area is not symmetric, where it goes up high like this, down like this, and then up like this, maybe, and then down like this. Something where the areas are clearly different from one side to the other side of the y-axis. So there's absolutely no reason why that would be a condition either. And then for 3, it talks about the graph of y equals minus f of minus x intersects the x-axis at the point x equals minus p and p only. So what have we got here then? We have, well, if we break it up into parts, we've got initially, if we look at y equals minus f of x, that is a reflection in the y-axis. So if we had points here minus p and p, and we reflected them in the y-axis, they would swap over, and p would go to minus p and minus p would go to p. So they would still end up with the two roots being in the opposite positions, but they would be the same roots. And then having done that, if you then have minus f of minus x, you then reflect it in the x-axis, and there is no change to the roots. The roots will stay the same. So in effect, by doing these two transformations, you end up really, it's a rotation of 180 degrees, and you end up with a p where the minus p is, and the minus p where the p is. So the graph intersects the x-axis at the points x equals minus p and x equals p only. Well, that's true. There were only two roots to start with. There's only two at the end. So that one is correct. And if we look at the choices, we now have which of the statements must be true. Well, it's the one where it's only three, which is D. So D is the answer to the question.